Hey, in this screencast, we're going to talk about the difference between open and closed systems, and it's not intuitive. So please take some good notes and pay attention. It's not a hard concept, but it's not an intuitive concept. Okay, so in order to apply the conservation of mechanical energy to a situation, it's necessary to define what the system is, what objects are part of the system, and which objects are not part of the system. Because only objects that are part of the system can have potential energy. So remember that a system is two or more objects that interact somehow. And an object is just something that basically we are not concerned with whatever its internal structure is. We only care about it as itself. So if I look at what I have here, I have two masses connected by a spring on a table that's on a floor. So I could say that these two things here, I'm just going to collectively refer to them as an object. There's a force acting on the object that's going to cause this object to accelerate and gain kinetic energy. Or I could say, well, I have a two object system. I have M1 and M2 and a spring. Okay. In that case, the spring has energy that can be stored up and released on these two objects. So where the spring force acts between two objects, which are part of the system. So I have an object spring system, all right? Or I could say, well, the earth is part of my system. So this is an object spring earth system, in which case these also have gravitational potential energy because the force of gravity exerted on this is by the earth, and the earth is part of our system. So I push this off the table, then it also releases gravitational potential energy. So we have to define what the system is in order to determine which components of the scenario involve conservative forces that can store and release potential energy. Right? So it's a little bit weird, but you'll get used to it. Okay, so let's just start with a single object system. If I have a single object system, I have a falling rock. I have an object pushed against a spring. If there's only one object in the system, then there can't be, then all forces are external, and therefore they do external work. Therefore, they change the mechanical energy of the system. So the only thing that can conserve forces is an internal force. If there's one object, all forces are external. So I have an object that is released in the air. Gravity is going to cause it to pick up speed as it moves through gravity. It's going to gain kinetic energy. But since the Earth isn't part of the system, I can't say that it had potential energy because that has to exist between two objects within a system. And since I didn't define the Earth as part of the system, it's just Earth is doing external work on it, causing it to gain kinetic energy, gain mechanical energy. Similarly, I have this box pushed against a spring. But my system is not a system, it's just an object, the box. When I let go of the box, the spring is going to do external work, causing the kinetic energy of the box to increase and causing the mechanical energy of the system to increase. On the other hand, if I have, say, an object Earth system, well, now I have two objects. I have the Earth and the object, and there is a force between them that is a conservative force, gravitation. Now I can have potential energy, at least gravitational potential energy. So I start off, the object has 0 joules of kinetic energy, but now it has 100 joules of gravitational potential energy because the Earth and the object are both part of the same system, and the force between them is a conservative force. So therefore, when I release, so I can say it to start off with, then it has, even though it's not moving, it has 100 joules of mechanical energy. And that will be conserved by this. So as long as there's no external force, say from air drag, as it falls towards the ground, it's going to lose gravitational potential energy. It's going to gain kinetic energy. Mechanical energy will be conserved. So we'll have still 100 joules of mechanical energy that it started with. But that's only if the Earth and the object are both part of the same system. So let's look at this. I have an Earth object system. I am not defining the spring as part of the system. Therefore, there's no such thing as spring potential energy. All right, so what happens is I have an object that has 0 joules of kinetic energy. It's the same height that was in the last example. It still has 100 joules of gravitational potential, and it has 100 joules of mechanical energy. Now, the potential energy is conserved between, the mechanical energy is conserved between the Earth and the object, but not the spring, because I didn't define the spring to be part of my system. So therefore, the spring is going to do external work on the system. So as this falls and compresses that spring, it now has 50 joules of kinetic energy. I said 0, it's not really at the ground, but let's just say 0 joules of gravitational potential energy. So it now only has 50 joules of mechanical energy. Not, I didn't conserve mechanical energy because the spring did external work on the system, in this case, reducing its mechanical energy. But if I define that spring to be part of the system, so now I have I'm sorry, no, in this case, I'm not defining the Earth to be part of it. I just have an object spring system. I didn't make the Earth part of it. So now I can have energy conserved between the spring and the object, but not between the Earth and the object, because I didn't define the Earth to be part of the same system. You see how this can be a little bit frustrating. So when you read prompts on the AP Physics test, you really, if it's about energy conservation, or momentum, as we'll see later in the year, you've got to be really careful about what we're considering to be in the system and not in the system. So in this case, since the Earth is not part of the system, I cannot have gravitational potential energy. I have two things in the system. I have this object and the spring. So it has 0 joules of kinetic energy, and it has 0 joules of gravitational potential energy because the Earth is not part of the system. So it has 0 mechanical energy. Now, as it falls, what's going to happen is it's going to gain gravitation can do external work on the system, causing it to gain kinetic energy. It's going to compress the spring. So the spring is going to gain 50 joules worth of spring energy, and it has 50 joules worth of kinetic energy. So the mechanical energy of the system went from 0, and in this point here, to 100 joules. So the system gained mechanical energy because of external work done by the gravitational force. So now let's make all of them part of it. Now I have a rock, earth, spring system, which is usually what they'll give you, but not always. You have to be careful. So now both the spring and gravitation can be considered to be conservative forces that can store up potential energy that contribute to our mechanical energy of the system. So I have an object that has 0 joules of kinetic energy. It has 0 joules of spring energy, but it has 100 joules of gravitational potential energy. Therefore, it has 100 joules of mechanical energy, even though it's not moving, because the Earth is defined to be part of the system. As this falls, the gravitational potential energy is going to go down and the kinetic is going to go up, and it's going to compress the spring. So at this point here, what I find is it's got 40 joules worth of kinetic energy. It's got 40 joules worth of spring potential energy, and it has 20 joules worth of gravitational potential energy. The mechanical energy of this system is conserved as long as there was no external force acting on it, like say drag. So it's frustrating, but it's not hard. You just have to look and see what we're including in the system and what we are not including in the system. And if we don't include it in the system, then you can't use that force to be something that you consider to be contributing to its potential energy. Now, let's talk about the difference between open and closed systems after I take a sip of coffee. So a closed system is one in which all the work is done by conservative forces, and therefore mechanical energy is completely conserved. It remains the same at all times within the system. An open system is one in which energy can come in or go out. There's force being done, there's external forces doing work on the system, and therefore the mechanical energy of the system is going to change over time. So we call that an open system. So closed, all the forces are conservative forces. They're spring. In the case of AP Physics 1, they're spring and gravitational forces only, and both the Earth and the spring and the object are part of our system. If it's an open system, that means usually the main non-conservative force we're going to deal with is friction. That's the main one we're going to look at. Or drag, air drag is another one that could do it. But also an applied force, a rocket, a hand. That's not a conservative force, so it's going to do work on a system. So let's look at a closed object spring system. So I have a stretched spring. So there is 100 joules worth of spring potential energy because this is stretched beyond its equilibrium point. They got 0 joules of kinetic energy, so it's got 100 joules of mechanical energy. When I let it go, it is going to gain kinetic energy. It's going to lose spring potential energy. If there's no friction, then the mechanical energy is going to equal 100. I have a closed system. The energy is completely conserved. There's no energy entering the system, and there's no energy leaving the system. It is a closed system. On the other hand, if I say, well, there is friction, and friction is an external force acting on this, it is a non-conservative force. It can't cause any storage of potential energy. So now what happens is I start off like I did before, with my object spring system, but I'm going to let friction do it. This is no longer a frictionless surface. So this friction force is going to do external work on the system. So I start off like I did before with 0 joules of kinetic, but 100 joules of spring potential. So I have 100 joules of mechanical energy. But as it slides forward now, I'm going to lose spring potential energy. I'm going to gain kinetic, but look, I only gained 100 joules of kinetic rather than 50. So I lost 50 joules of spring potential energy, but I didn't gain 50 joules worth of kinetic energy because energy left the system. 40 joules. Look, I now only have 60 joules worth of mechanical energy. That means the force of friction, which is an external force on the system, it basically did 40 joules worth of negative work and took 40 joules of mechanical energy out of the system, which will then be dissipated as heat. So you got to get used to that idea. Friction makes things hot. And when things are hot, the atoms wiggle and they make infrared light, and that infrared light goes off in all directions. And conduction between atomic particles causes them to spread energy outward. So friction causes thermal energy, and thermal energy dissipates. So we often refer to friction causing energy to be dissipated out of the system. Well, now let's look at a system here. So here I've got a satellite in elliptical orbit. So in an elliptical orbit, so rather than a circular orbit, I have the object here. It's far away. Let's just say this is a satellite. This is the Earth. Okay, I'm far away from the Earth. So here I have a small amount of kinetic energy, but I've got a lot of gravitational potential energy. I'm far away. Now, as this goes around and it comes by here, it's losing potential energy. And since there's no friction in space, it's going to gain kinetic energy. So whatever the mechanical energy is here, the mechanical energy is going to have to be here. This is a closed system. There's no place for the energy to go. And so since I haven't added or taken energy out of it, the total mechanical energy of the system is going to remain constant. It is a closed system. But what if I had a rocket engine? Now that rocket is applied force. This isn't friction, but it's basically an applied force from the rocket thrust. And that's going to do work on the system. It's going to change the mechanical energy of the system. So therefore, it's no longer a closed system. So in this case, let's say the rocket is going to do negative work. So I start off what I had before. I have the I have gravitational potential energy, and I have a little bit of kinetic energy, and I'm moving this way. So I'm going to apply a rocket thrust. So I'm pushing the satellite against its motion. So what that's going to do is it's going to make it slower. So it's not going to end up here. It's going to end up closer. What's going to happen is my ellipse is going to shrink a bit. Now what happens is I've lost uh, gravitational potential energy, so I'm going to gain kinetic, but I'm not going to gain as much as I would have otherwise. So I've lost some work. I took energy. I mean, I did negative work. I lost energy. So the mechanical energy of the system here is going to be less than what it was before. Before this was moving at a greater speed. Now it's going to be going at a slower speed. So this system is now open. Energy has left the system because of that rocket thrust took energy out of the system, mechanical energy out of the system. All right. So hopefully you can follow along with that. We'll practice this a lot and you'll get comfortable with it if you're not comfortable with it right now.